have the pleasure to welcome you at GSI. GSI is a Helmholtz Center for Heavy Iron Research, and most of you have probably never been here, and for you I have prepared a short presentation on what GSI is, what FAIR is, what Helmholtz is. My name is Peter Spiller. I'm heading the sub-project SIS100, SIS18. Germans like long names. SIS is the German name for Schwerionensynchrotron, which means heavy iron synchrotron. These are the big circular accelerator in the north of our accelerator facility. And the 18 stands for the magnetic rigidity, and the 100 is also the magnetic rigidity of the big new machine that we are presently going to build. And I will show you a little bit what GSI is, what FAIR is. I have not much time, so a brief presentation on the basic or fundamental things we are doing here. So this is a map of Germany, as you are almost in the middle. And the Helmholtz Association is the biggest research organization in Germany. So there is, as you can see on the left side, about 50,000 employees, about 6 billion euro annual budget, 18 large-scale research centers, and many, many international users. Of course, you don't build very expensive machines and facilities only for the few experimentalists you have in-house. Usually there's broad communities worldwide who are going to use your facility. This is also what, of course, basis is for building FAIR, our new big project in the east of GSI. Is an expensive, large-scale facility, and that's one of the mission of the Helmholtz Association, to build large-scale facilities or large-scale experiments, like polar ships, high-field magnet laboratory, big accelerators, fusion experiments, tokamak, accelerator, and things like that. So the organizations have different purposes. You see there's coastal research, polar research, climate research, aeronautics and space, plasma physics, fusion, of course, environment, materials, energy, cancer research. So all of these topics are addressed by the Helmholtz Association. We are at GSI. GSI is the part of the buildings which are completed here on the lower left side. You are exactly here. No, you are here. Sorry, this is the new building that we are going to use for controlling our new accelerators in the east of GSI, the new control center building. And the upper part shows you the construction site. Is a little bit older picture of the FAIR project. So this is GSI, the Helmholtz Center for Heavy Iron Research. Exists since 1969, where it was founded. This is more or less the national facility. 80% of the budget or a bit more comes from the federal government, and the state, usually for the Helmholtz Center, the local state covers about 10% of the annual budget. We have 2 Helmholtz institutes in Mainz and Jena. These are towns in Germany we probably don't know. And yeah, we proposed a new project, a new facility. Actually, 2001 we wrote the conceptual design report, so this is already a 20 years old story. And about 1,500 people who are working here at GSI. So we call ourselves universe in the laboratory. So we explore the universe in the lab. Actually, we are also ground lab of ESA, because we can generate with the heavy ion beams conditions which are relevant for radiobiology or for astronauts flying to the Mars, for instance. So the basic question, what are smallest building blocks in matter? How and where are they created? How are the chemical elements formed in stellar explosions? What does matter look like in most heavy objects in the universe, neutron stars, things like that. Yeah? The point is we can create these exotic states of matter in the lab here at GSI by using the heavy ion beam or the ion beam made from the accelerator facility. You see 2 colliding nuclei here, and in a short moment in time you generate exotic matter that you find elsewhere. It's very seldom on this planet, but in universe, exotic state of matter, extreme forces, for instance, at colliding neutron stars and things like that. So that's GSI, the facility which has been, which exists, which are running. There's a user program. Machines are booked out for several years in advance. Besides the big project, we have to deal with that as well. So we have to maintain the machine, we have to upgrade the machine, we have to run the machines for the users. Of course, the user time is a little bit reduced because we are all totally overloaded. We all work for the experiments which are conducted here at GSI, but we also in parallel realize the big machines in the East. So there's several ion sources. We have a broad flexibility in producing beams, different ion species, from protons to uranium. We can accelerate all ions. And for that, with different parameters, in a time-sharing mode, we run up to 6 experiments in parallel in a time-sharing mode, serving with usually 3 different ion species, making beams of different ion species. For the experiments, and the first stage in acceleration is a linear accelerator. UNILAC is a universal linear accelerator. It's a very old machine, but still the most powerful heavy ion LINAC worldwide. And this machine serves experiments in this first experimental hall, which was built in the 17th. There's nuclear physics experiments possible since 20% of speed of light is already achieved. And then you accelerate further in the ring accelerator SIS18 up to 90% of speed of light, depending on the ion species, of course. Then we have some sophisticated experiments, which are also basically accelerator sections, the called fragment separator, where we can separate nuclear fragments in a kind of mass spectrometer and inject these rare isotope beams into storage rings, or transport the primary beam or secondary beam to experimental areas. And we have a smaller ring, new storage ring called cryring. This is a facility that runs and where we do experiments. This is how it looks like. This is an old picture of the UNILAC. The circular accelerator looks a little bit different, of course. So these are quite big machines, a lot of technology, and GSI is doing experiments since decades. So we have well-organized way how to select proposals for using the machines for the experiments and plan the beam times. So that is, I always tell my boss is a managing director, don't tell the politicians only about exotic particles which they don't understand at all. So they would tell you this is no meaning for society. They may say that sounds interesting, but what it is good for we give you billions of euro. So we do a lot of technology development here. We have actually a technology transfer department here. And there's, of course, lots of opportunities for applications. We have a superconducting magnet department. We are developing fast-jump superconducting magnets, and now we say we build an AC energy cable, superconducting energy cable, for instance. We are able to find faults in superconducting busbar systems with a precision of sub-millimeter, and now we say we save critical infrastructure. We apply this technology to undersea, underground or underwater cable in the sea lying between, let's say, Sweden and Germany, and we can detect the fault in 200 kilometer difference with a precision of a centimeter. This presently we show the companies that we are able doing that. So there is a lot of applications possible. Of course, usually scientists don't think in applications. They are, I mean, you know this. They work in their own universe up to 12 o'clock midnight, and usually you have to tell them, please look also for applications, and there's lots of applications, and this is what, of course, politicians like. One of the applications we have developed a cancer therapy. Here at GSI, built a pilot facility and treated about 400 people here. with heavy ion beams. And since this has severe or significant advantages compared to the standard radiotherapy you get in a standard hospital, in terms of precision, in the spatial distribution of the dose that you deposit in the cancer or in the tissue. This is a success story. In Heidelberg, we have built a small accelerator for the clinic, and they treat about 1,500 patients annually, and works perfect. And this is, of course, something where our funding agencies say, something relevant for the society. So GSI is still involved in improving this technology, for instance, improving the structure of the slowly extracted beam, or enabling further parallel operation, which increases the efficiency of using the facility in Heidelberg. This is one of our technology transfer stories. Yeah. We also discovered a number of new heavy elements, which you find probably in the school book meanwhile. And since we discovered them, we were allowed to give them names. One is called Darmstadtium for the town here nearby, or Hassium for the state of Hessen. So this is nuclear physics. And we, with the fragment separator, generate huge amount of nuclei far away from the line of stable elements, and discover the processes how, for instance, the heavy elements are generated in exploding star supernova or in normal solar life cycle. So the FAIR project is a unique facility because while others accelerate electron and proton beams, actually there's different communities in the accelerator field. Most of them build machines for proton electrons. Our focus is heavy ions, and there where I always say we have the best in making machines for heavy ions. For uranium beam, we have to be world leading, for instance. Yeah? So our machines are always optimized for heavy ions or for heavy fragments, which you produce within a collision with the target. So we form exotic nuclei, do basic research, and as I said, we don't build these machines, of course, only for the experimental groups we have at GSI. We have experimental departments here, but of course, usually in these different areas of science, there are international collaborations which are using the facilities. So this is 5 times larger. The red part is what we are going to build. You have the opportunity to visit the construction site. The SIS100 is a machine which is about 1 kilometer in circumference. It's not the biggest machine, but this is a machine which is unique in terms of acceleration of highest intensity of heavy ion beams. This is a special design. We have invented new technologies, new lattice structures in order to be able to generate beams with the highest intensity of heavy ions. Then we have the big brother, so to say, from the fragment separator is our super fragment separator, then, which consists of a radiation hard magnet part and superconducting magnet part. And depending on the funding, of course, then we will further on extend the facility to collector and energy storage rings to be able to digest anti-proton beams that we are going to generate from the proton beam in an anti-proton production target. This is the next goal after we have completed, we call that modularized start version 0 to 3. This is up to here, comprising the NUSJA, nuclear physics, nuclear structure physics, and the compressed baryonic physics experiment, compressed matter experiment. This is what we can build with our present budget, but there is lots of opportunities here for further upgrade. So we are aiming for the highest intensities. Beam quality is always a topic which I cannot address in detail here, because concerns a lot, of course, on how much of the produced beam you can effectively use for your experiment, and this is our goal. So this facility is part of the European research roadmap and priority in the nuclear physics community. So this is the biggest, let's say, project serving the nuclear physics community in Europe. The FAIR project was suggested by us, but GSI, or Germany, is now only one of 10 shareholders. This is an international project now, and there's contributions from all over the world. Actually, the biggest contribution originally was from Russia, and due to the Ukraine topic, several contracts have been terminated, and there's only one collaboration left. But there's many other contributions. Poland, big contribution, India, for instance, and this comes as in-kind contributions at most in terms of components. So we specify the components, and these countries basically develop and deliver the components for the machines and experiments. And communities we have already addressed. This is clear. There's the scientific collaborations which consist of contributions or comprised of partners from many worldwide leading centers, of course. FAIR is huge, a big project, one of the biggest science projects in Europe. This is some impressive numbers. 2 million cubic meter of earth are moved, 600,000 cubic meter concrete are built. Actually, the shell construction is completed from the buildings, and a lot of steel for the reinforcement of the concrete. Partly we have wall thickness of 6 meters with a lot of steel inside for shielding purposes. Because FAIR is situated in area which is partly then afterwards, after we have completed the facility, still public. So we are in the phase of procuring the accelerator components since several years. Actually, lots of components have been delivered. We have huge storage areas. One big storage area nearby is now full. We have had to rent a new storage area in order to digest all the deliveries. On the right side, you see some superconducting dipole magnets for SIS100 or cavities or local cryogenic systems for distributing the helium over the facility. Yeah, and actually for the high energy storage ring, which unfortunately because of budget constraints we cannot realize presently, the money for the building is missing. The machine components are already delivered to a large extent. So this is, let's say, an internal management issue. But most of the accelerator components, or big fraction at least, is delivered, and we have started installation early this year. In January, we have brought the first machine components into the SIS100 tunnel. So a lot of high tech. I mean, you know this story is clear. Superconducting magnets, cryogenics, extreme vacuum is required for the heavy ions, much more demanding than for the acceleration of protons or electron beams, because heavy ions usually have the tendency to change their charge state when they collide with residual gas atoms in the vacuum system. So there is a lot of high-tech development, and we have GSI have lots of technical departments who usually do a very good job here, and we have lots of collaborations, of course, helping us to develop this hardware for the machine. So that is a short introduction in where you are and what we are doing here. Accelerator lab, typical, and I'm not sure if you have ever been at an accelerator laboratory. You have a tour, I guess, also through the accelerator facility and through the buildings. As I said, shell construction is completed. The building infrastructure is being integrated. Cable planning, cable laying is a big issue. 7,000 kilometers of cable, big story, and you get an impression. And I wish you a successful workshop. Lots of new opportunities, of course. Hopefully also you can establish some new collaborations here. So welcome at GSI.